Good afternoon. My name is Pritam Shah, and today I'm going to present the paper Learning Augmented Maximum Independence Set by Braverman, Dharan Dute, and the other co-authors. The topic is the maximum independence set problem, a classic hard problem in graph theory, but here we look at it through the lens of learning augmented algorithms. That means the algorithm gets a noisy hint from an oracle about which vertices are in the maximum independence set. Our goal is to see how we can design algorithms that use this imperfect hints to get probably better approximation than classical worst case algorithms. The main motivation behind this problem was the maximum independence set problem is well known to be a NP-hard, and even approximating it within a factor of n to the power 1 minus delta uh, uh, for any number where n is greater than 0 and delta is greater than 0 is also NP-hard in general graphs. In the worst case world, that's a dead end, but in practice when you run heuristics algorithm like query selections or local search on real world networks, we often get solutions close to optimal. Why does that happen? Usually because real graphs have patterns, communities, degree distributions, or other structures that we can exploit. Now imagine we have a machine learning model that's been trained on similar graphs and can predict for each vertex whether it belongs to the maximum independent set. It's not perfect. Maybe it's the right only slightly more than half the time, but could we still use those predictions to design algorithm with strong theoretical guarantees? That's the central question of this work. Now, for the Oracle model, uh, the paper models predictions using that they call an maximum independent set oracle denoted uh, by GI of V for a fixed uh, for the fixed maximum independent set I star. The oracle answers whether V belongs to I star with probability of half plus epsilon. Here's how it works. We have some fixed but unknown maximum independent set. If we ask the oracle about a vertex V, it answers yes with a probability of half plus epsilon. If V is really is in I star, and yes with the probability half minus half, and or half minus epsilon otherwise. So epsilon is our bias. The bigger it is, the more accurate the oracle. We consider two noise settings here. Persistent noise is vertex answer is determined once at the start. No matter how many times you ask, you will get the same level. Non-persistent noise, the second option, which explains each time you query, you get a fresh random answer from the distribution. That means you can requery and average the results. These two models capture different real-world situations. Persistent noise is like a fixed ML model making one prediction per vertex, while non-persistent noise is like being able to run a randomized prediction model multiple times. And the main result was the persistent noise for the theorem 1. The persistent noise model, they give an algorithm that makes exactly one query per vertex, so we can't refine our estimate by resampling. The algorithm runs in O of m time that outputs an independent set uh, with uh, uh, with a modulus of I greater than epsilon by 12 dot delta of ln n to the power minus half dot modulus of I star. Linear in the number of edges and returns an independent set that has the high probability uh, where delta is the maximum degree of the graph, and this means the approximation ratio is roughly uh, O of square root of delta divided by epsilon. If delta is small, then epsilon is not tiny. This is much better than the worst case bounds. Uh, but for the non-persistent noise, which is basically theorem 2, the main result uh, is we can query vertices multiple times to reduce noise. The algorithm uses a total of only O of n divided by E epsilon square, the total width, and the O of m time that returns an independent set I, with where I modulus of I is greater than 48 divided by 50 times. I star with high probability. That's a linear number of vertices and still runs in near linear time in n with high probability. It outputs an independent set whose size is at least this. Uh, that's a 96% approximation ratio. This is a big jump in quality, and it's achieved without excessive queries thanks to the clever query allocation strategy. The core idea of persistent noise, that's basically neighborhood aggregation. In persistent noise, a single wrong prediction can be fixed by resampling. So instead of trusting the oracle's prediction for vertex, we directly we look at the predictions for all the neighbors. Uh, for all the neighbors of n of v, if many of these neighbors are predicted to be in the maximum independent set, that's strongly evident that v itself is not in the maximum independent set, because independent sets cannot contain adjacent vertices. This aggregated neighborhood statistic is more robust to noise even if a few neighbor levels are wrong. The majority trend still carries a useful information. Now for the persistent, the algorithm wants case for every v computing the degree of v, the number of neighbors, the oracle's levels, which is basically yes. And in the step 2, let the L is equals to v such that v is of degree v less than or equal to 36 logarithm of n in lower degree. Uh, the v is number of the neighbors that oracle predicts as yes. Now in the step 3, the let s is equals to v not belongs to L such that degree of v is less than sv, where is v the threshold depending on degree v. For higher degree vertices, keep them only if their neighbor yes count is below a threshold that depends on their degree. Run a greedy maximum independent set algorithm on this reduced graph. Uh, by using Chernoff bounds, they proved that almost all real maximum independent set vertices survive the filtering step, while many non-maximum independent set vertices are eliminated. The core idea behind the non-persistent algorithm is elimination and vertex cover. In the non-persistent model, we can use repeated queries to reduce uncertainty. The algorithm works in elimination rounds inspired by multi-armed bandit strategy. In each round, we query each vertex a certain number of times. If fewer than half the answers are yes, we remove the vertex. It's unlikely to be in the MIS. After several rounds, the most non-maximum independent set vertices are gone. Then we compute a two approximate vertex cover on the remaining graph using a maximal matching. The complement of the vertex cover is guaranteed to be an independent set, and in this context it's large and close to the optimal maximum independent set. The algorithm 2, which is non-persistent, is in detail. The pseudocode is here. First we assign the v to v0, and in the range from for r1 to 2 we continue for each v belongs to v r minus 1. Then we continue the loop for query is the v for the qr is equals to 4 epsilon square times r plus logarithm of 1 divided by delta times. Uh, we remove the vertices with a fewer than half yes response, compute a two approximate vertex cover on survivors, and take each complement as an independent set candidate. Then we track the largest independent set found over the rounds. The query schedule is tuned so the total number of queries is uh, total number of queries is qr divided by 2, and it exceeds the budget of n divided by epsilon square and times logarithm of 1 divided by delta, ensuring efficiency. By the end, with the high probability, the output is at least 96% of the size of the true maximum independent set problem. Uh, Now, in the persistent setting, can we beat the lower bounds? It's basically still unknown. Can we do even better with the sublinear queries, fewer than in total queries? In practice, how do we build oracles that achieve a reasonable? Graph neural networks and heuristics maximum independence set solvers are promising candidates. The big takeaway is that even a slightly biased prediction oracle, say only 55% accurate, can be leveraged to get provable gains on a problem that's extremely hard. In the worst case, that's exciting because it bridges worst case complexity and practical performance, showing how much machine learning can meaningfully enhance classical algorithms. Thank you.